Takeoff and landing performance charts. This is a topic that cannot be taught without using an actual example. So let's get on with it. Let's get Pilot Chintan Patel to work. Alright, so now let's take a look at how to use takeoff performance and landing performance charts. We already learned how to use a takeoff table, when we were talking about the effects of winds on takeoff in the previous video. So now what we are going to do is we are going to learn about how to use a graph. For this, we are going to take a landing graph. A landing graph and a takeoff performance graph are pretty similar in how to use them. So let's just get started with this landing graph. For simplicity, we are going to use the sample given in the landing graph itself so that it is easier and much more clear for us to follow. Alright guys, take a look at this graph that I was talking about. This is the landing distance ground roll graph above 17,000 kg for this particular aircraft. On the bottom left corner of the first box on the left, you see an example. It talks about pressure altitude of 0 feet outside a temperature of 15 degrees Celsius, mass of 1750 kg, and headwind component of 10 knots. Let's see how we can use this information and this graph to get our required performance values. First, start from the leftmost box or leftmost values in any graph. In our case, on the x-axis you see outside air temperature. We need to find our outside air temperature, that is 15 degrees Celsius now. That 15 degrees Celsius, start a line upwards perpendicular to 15 degrees Celsius line. Elongate the line until it meets your pressure altitude, that is 0 feet. Once it hits 0 feet, get that intersection point and draw a line horizontally towards your right and head over to the next box. As you can see, as soon as you reach the next box is about the landing mass. Now, draw a line from your landing mass, that is 1750 kg, from the x-axis on the bottom all the way up, and now start your line from the left along the contours to meet the 1750 kg line. Whatever intersection point you get, draw a horizontal line towards your right. Now, important thing here is to follow the slope or follow the contour. You have to be along the lines that are sloping downwards in the landing mass graph. Now that you have reached the wind components table, you again have two contours or slopes, one sloping downwards and the other sloping upwards. The bunch of slopes downwards are for headwind and bunch of slopes upwards are for tailwind. We have a 10 knot headwind component, so we need to use the sloping down lines. We follow the slope which is nearest to us and follow down until we reach our 10 knots elongated headwind component line upwards. As you can see, I'm highlighting that point. As soon as you get that intersection point, draw a line from that point parallel to your x-axis towards your right. On the right, you see a scale for landing distance roll. This particular graph talks about landing distance roll in meter and feet as well. Wherever your line intersects the landing distance ground roll scale is your landing distance ground roll. That's it. That's pretty much it. You read the conditions below, which requires flaps, power both of the engines idle because it's a multi-engine airplane. Runway level and hard, dry surface, approach speed 78 knots indicated airspeed. Some pilot operating handbooks recommend specific approach speeds for various flap settings and aircraft weights. In general, these recommended airspeeds should be used regardless of the temperature and altitude combinations. As you recall, operating at higher density altitudes will result in higher than normal true airspeeds. This is important to remember when landing at airports that have a higher airport elevation than the ones you are normally accustomed with, because higher ground speeds can cause you to fly ridiculously slow, low airspeeds, and and you will operate closer to stalling speeds. This effect is the same effect or a similar effect as the downwind landing we discussed earlier.